Imagine you are playing a modified version of the classic board game GuessWho. Two players sit across two different computer screens. A grid of faces pops up, one out of which is secretly chosen. The challenge? Figure out your chosen card using the minimum number of questions. First, a secret card is assigned. Then, every turn you can ask a yes or no question, like does your person have long hair? Are they wearing a hat? And so on. The eliminated cards are instantly grayed out on the screen. Question by question, you narrow it down until there's only one card left, and that's your answer. Your score is the total number of questions taken to reach the answer. The player with the lower score wins, or it's a draw. We've made 3 tweaks to the original game to keep things fair and to keep the math simple. First, no peeking. In the board game, you can glance over and see how many faces your opponent has flipped down. That tells you if they're close to winning. Here, you can't. Second, draws are possible. Normally, the first player has an unfair advantage. In our version, if both players find their card in the same number of questions, it's simply a draw. And finally, the big mathematical simplification. You can ask if the card lies in a given subset, not just glasses or no glasses. This allows us to treat the faces as numbered cards. With the rules clear, let's dive into the strategy. Let's say you have 12 faces in front of you. What's the first question you'll ask? I'll give you a moment to think. Well, a very good strategy will be binary search. The idea is to always ask a question that splits the remaining possibilities into two groups of nearly equal size. With 12 faces, you want a question that creates two sets of 6. A great first question could be, is the number even? Or is the number composite? Or is the number less than or equal to 6? All of these divide the faces into two equal sets of 6, guaranteeing maximum progress. Here we see binary search in action. With each question, the number of possibilities is cut almost perfectly in half. This is mathematically the fastest way to shrink the search space, guaranteeing the answer with the minimum number of questions on average. We can think of any search strategy as a decision tree. A node represents a search range interval. Every time we ask a question, we go down one of two branches, depending on the answer, until we are left with a single card. The depth of a leaf represents the number of questions needed to find it. The overall performance of a tree is measured by its expected depth. Of course, binary search isn't the only strategy. Any valid sequence of questions forms a tree, like the two different structures you see on the right. The binary search tree on the left has a lower expected depth. In fact, it's a mathematical guarantee that the binary search always minimizes the average number of questions. So, binary search is the optimal strategy. Or is it? Because the goal isn't just to minimize the score, it's to beat your opponent. Let's think about the question. What's the best way to represent a strategy? Clearly, the list of leaf node depths is enough to evaluate the performance of the strategy. We can group and reduce them to a histogram. Let's call this the depth histogram. This serves as a compact summary of the original strategy tree. We want to answer a fundamental question. How do two different strategies compete against each other? Specifically, What are the exact probabilities of win, loss, and draw? To answer it, let's first convert the trees into depth histograms. These are then combined to form a 2D probability space. Within this space, specific regions correspond to win, loss, and draw outcomes, with the area of each region representing its probability. The outcomes can be seen on the screen. To validate this analytical model, we conduct a Monte Carlo simulation. In each trial, we select a random leaf from each strategy's tree and compare their depths to determine the winner. Let's speed this up to 20,000 simulations. The simulation confirms our calculation. In order to evaluate match strategies, we need to map the win-loss draw probabilities to a single score. How do we do it? A simple way to do it is to assign points 0 for a loss, half for a draw, and 1 for a win. Here we see that for P win 0.5, P draw 0.2, and P loss 0.3, the expected score turns out to be 0.6. This score summarizes how well a strategy performs against another. Here we find a complete list of all search strategies for 6 phases. These are generated using a simple recursion program. They are color coded so that trees with similar depth profiles share the same color. We transform these strategies into depth histograms. Remember, the histogram is a summary of a strategy's performance. As we do this, we can merge the duplicates. This leaves us with just 5 unique strategies. Next, we sort them by their score, from best to worst. The strategy on the far left now has the lowest average depth, making it the most efficient on paper. But how do they compete in a head-to-head match? To find out, we transform the strategies into a matchup matrix. Let's see how each strategy fares against other strategies. We see that the top strategy, which is binary search, consistently wins. It beats every other strategy. So let's call this the dominant strategy. The question is, will this always be true? Will the binary search always be able to beat all other strategies? For n equal to 7, we have a total of 8 strategies. We can see that the top strategy, which is binary search, beats all other strategies. So it's always optimal to use binary search. For n equals to 8, we have 16 strategies. Again, binary search, which is the top strategy, wins against all other strategies. So no surprises here. For n equals to 9, the number of possible strategies grows to 28. To keep the analysis clean, we focus only on the top strategies. All the others are dominated by the top strategy, so we ignore them. Once again, we see that the top strategy beats all others. At n equals 10, we'll again zoom into the top strategies to keep the analysis simple. And here we find our first major surprise. The top ranked strategy, the binary search, is no longer dominant. It's beaten by strategy 3. This new strategy, a slightly skewed tree, doesn't just beat binary search. It wins against every other strategy, making it dominant. Isn't it amazing? The fact that the best way to split 10 cards is not 5-5, but 6-4. For n equals to 11, we have a total of 89 strategies. When we zoom into the matchup matrix for the top contenders, we see something new. There is no single row without any red. This means that, unlike our previous examples, there's no single dominant strategy. So, how do we find the best play? We start by simplifying the game. We can find some strategies that are guaranteed to perform worse than others. For example, strategy 2 has a worse score than strategy 1 for every possible column. So, we say that strategy 2 is dominated by strategy 1. It never makes sense to play a dominated strategy, so we can remove them entirely. After filtering out all the dominated strategies, we are left with just 4. When we look at their 4x4 matrix, we see none of the 4 strategies dominates the others. Instead, they form a cycle, like a complex game of rock, paper, and scissors. There is no single safe or best choice. So, what do? This is where the game gets really interesting. This is the payoff matrix from the previous example. It represents the scores when two players are playing with different strategies. No matter what option you choose, your opponent can select a counter move that gives them better odds of winning. So, what do you do in this case? The solution is to introduce some randomness in our strategy. Let's represent the probability of choosing action I as Pi. This essentially the equations on the left calculate our expected payoff for each of the opponent's possible actions. We want to maximize the worst case payoff. We'll call this the guaranteed minimum payoff V. Our objective is to find the probability distribution P that makes this guaranteed payoff V as high as possible. This type of optimization problem is very common in fields like economics and computer science. It's known as a linear programming problem. So, how do we solve this? The standard way to solve such problems is to use the simplex method. This algorithm works by navigating the edges of a high-dimensional shape that represents the solution space. It explores the corners until it finds the optimal one. I won't go into the details of the simplex in this video, but I'll leave a link in the description if you are interested in learning more. When we run simplex, we get this solution. Using this specific mix, you can guarantee a win probability of at least 50%, no matter what the opponent does. But remember, this is a symmetric game, so your opponent can do the exact same thing. What happens if both players follow this strategy? Neither player can do better. This stable state is called a Nash equilibrium. Here, no player has an incentive to change their choice. After all these trees, histograms, and matrices, what have we actually learned? We started with a very intuitive idea that the best strategy is the most efficient one, binary search. And yet, that idea was wrong. We found that in a direct computation, a less efficient strategy could win more often, simply by taking more risks. And then we found situations where there was no single best strategy, where any fixed plan you commit to can be studied, predicted, and ultimately defeated. What do when any choice you make is exploitable? You refuse to choose. You play them all with carefully chosen probabilities. This isn't a quirk of our game, it's a fundamental principle of strategy. Random strategies are used for better performance in games like rock, paper, scissors, poker, and football penalty kicks. Whenever an opponent can adapt to your tendencies, the solution is to have no tendencies. The optimal strategy is a mix of strategies. GuessWho, a game of simple questions and faces, turns out to be a beautiful window into one of the core ideas of game theory that, in a competitive world, the key to victory isn't always finding a perfect plan, it's about becoming unpredictable. Thanks for watching.